the left-hand side represents the gravitational degrees of freedom, and the right-hand side represents matter. There will be two different models of matter that I'm going to consider in this talk. The first example is, again, very familiar, where T is identically equal to 0. That's the vacuum case. And you will see that for reasons that I'm going to explain a little later, that will be considered in dimensions. This will be relevant in dimensions bigger than or equal than 10. And then the second model that I will consider is going to be the scalar field, where the energy momentum tensor of matter is given by, again, a familiar expression that I'm going to write down nonetheless. So this is just a real scalar field function, which itself satisfies the wave equation on the background determined by the metric G. Okay, so these are two models. Now, what about the manifold M? So I already mentioned that I'm going to be considering it in d dimensions. One relevant dimension is going to be 10. And of course, the other relevant dimension is going to be 3. So the scalar field model will be considered in dimensions bigger than or equal than 3. So this is this. Now, the topology, I'm going to take the case when this is for, after all, for cosmology reasons, M is going to be spatially compact. And in fact, you can simply think that this is going to be a product of a d-dimensional torus times an interval, where the interval is going to be play the role of time. So the topology is simply the torus topology in dimension d. Okay, very good. So now let me remind you how to write down the Einstein equations as an evolution equation in relative to the what's called the 3+1-dimensional split. Of course, in this case, this will be the D+1-dimensional split. So D+1 split. Again, you imagine that you have a time function t. You imagine that M, the manifold, is foliated by the level surfaces of function t. So these are sigma t's. I'm going to prescribe our initial data somewhere here, sigma naught. And then the basic objects that we're going to try to understand is the evolution of the metric and the second fundamental form associated with the foliation sigma t. So the metric is going to be written in the form g alpha beta is minus the lapse function squared plus the spatial part of the metric. The second fundamental form, Kij, is simply defined as minus 1/2n time derivative of Gij. And we can write down our Einstein equations in the following form. So one equation is already written. You can think of it as an evolution equation for the spatial part of the metric Gij. And the other part, the second evolution equation, tells us how the second fundamental form evolves, and that is dt Kij is equal to minus di dj lapse function plus lapse times the following expression. So it's going to be Ricci curvature of the 4-dimensional metric plus the Ricci curvature of the 3-dimensional metric Gij minus trace of the second fundamental form Kij minus, plus minus 2 Ka. Okay. Right. So this, you can think of this equation as telling you how the second fundamental form evolves. And on the right-hand side, you see either Ricci curvature, which is supposed to be determined from the Einstein equation. So this is determined from the energy momentum tensor of matter. In the vacuum case, this term is simply equal to 0. And then this is the 3-dimensional geometry of the slices sigma t. Very good. And then, of course, we have to supplement this with constraint equations. So constraints. So the first constraint is the so-called Hamiltonian constraint, is three-dimensional scalar curvature minus k squared plus trace k squared is equal to, again, something which has to do with Ricci curvature of the four-dimensional metric. So in vacuum, the right-hand side is equal to 0. And the momentum constraint is J minus trace K. And again, something that has to do with the Ricci curvature of the four-dimensional metric. That's it. So given the initial data that satisfy constraints, you can evolve our spatial metric Gij. You have the lapse. Didn't write the equation for the lapse itself because that requires fixing a particular gauge that I'm not going to tell you about right now. It's going to come up later. And you evolve the second fundamental form, and you can obtain your evolution at future times if you're evolving this problem to the future. Very good. So what happens when you evolve this problem to the future? Well, there's a whole zoo of phenomena that can happen when you evolve this problem to the future. But I'm interested in the situation where singularities may form in the future when you evolve your initial data. So there are specific situations where some sort of singularities are predicted by general theorems. And I'm going to remind you of one of such situations, and that is the Hawking incompleteness theorem, also popularly known as the Hawking singularity theorem. But it actually does not predict the singularity, it just predicts incompleteness. So incompleteness theorem, which is tailor-made for the situation that we are considering. So what are the conditions? Well, we need the strong energy condition. So that's just an assumption on the matter model that we're considering. Both the scalar field and vacuum satisfy this assumption. Strong energy condition. We need to know that we spatially compact. So let's say sigma naught spatially compact, which is exactly the situation that we're considering here, where sigma naught is simply a torus, spatially compact. And then we need the final condition that when we look at the trace of the second fundamental form K on sigma naught, then it has a sign and it's strictly positive. Sigma naught. And what is the conclusion? Well, the conclusion is that in this case, we have future geodesic incompleteness. Excellent. Very good. But does this correspond to a singularity? And this theorem gives you absolutely no answer to what causes this geodesic incompleteness. Thankfully, we do have examples. So I do want to talk about examples. In fact, explicit examples which satisfy the assumptions of Hawking incompleteness theorem and actually tell you that there will be a singularity in the future, and it's an interesting singularity. So all right. So examples. These are so-called Kasner solutions. So let me start with vacuum first. So when T is equal to 0, again, we can write this metric explicitly. The metric G is simply of the following form, minus dt squared plus the sum. This is in d dimensions. So it's sum of t to the power 2 pi dxi squared. So you see that the lapse is equal to 1. The spatial geometry is flat. So the only parameters that we have in this problem are the constants pi's, where I runs from 1 to d. And it turns out that if you look at the Einstein equations, and basically you just need to satisfy the constraints in this case, then you see that this parameters pi should satisfy two relations. Their sum, as well as the sum of their squares, should be equal to 1. And if that's the case, then any such metric is a solution of the Einstein vacuum equations. And moreover, there are a couple of things to notice. One is that this spacetime does satisfy the assumptions of the Hawking incompleteness theorem if you compute the trace of the second fundamental form, you'll immediately see that it's actually equal to -1/t. So when you impose initial data at time t equals -1, you see that trace is positive. And so you can then read off from the metric itself, you see that the metric collapses at t equals 0. So at t equals 0, we have a singularity. Moreover, it's a strong singularity in the sense that we can actually compute how strong the Kreshman scalar, for instance, blows up. And we see that the Kreshman scalar behaves like constant divided by t to the power of 4. So this is a space-like singularity. Every point on the torus, on our torus, collapses to the future, and we can compute the strength of the singularity. Very good. Now, one thing to notice immediately is that our constraints on the parameters pi are pretty severe. So one thing that you see immediately from here is that the absolute values of pi's should all be less than 1. And another consequence is that at least one of these pi's has to be negative. So for instance, at least p1 has to be negative. Otherwise, we cannot satisfy these constraints, which is interesting because it tells you that not every direction collapses. There are some directions that are actually expanding that you go to the singularity. Very good. Now, what happens when you add the scalar field? So this was vacuum. Now, when you add the scalar field, so this is the first example, and now the scalar field. So we can actually, again, write down a family of solutions explicitly. We're going to simply postulate that the scalar field is equal to some constant b times log of t. And then the metric is again in the same form with Kasner exponents pi's, but now pi satisfies slightly different condition. Their sum is still 1, but their sum of squares is no longer required to be also equal to 1. It's actually now equal to 1 minus b squared. So we have one extra parameter, and that extra parameter is the amplitude of the scalar field, which of course itself blows up at time t equals 0, but the constant in front of that blow up, in front of the log, allows us to more flexibility with the Kasner parameters pi's. So in particular, it turns out that in this case that we can make all pi's to be positive. And that's an important consideration from what I'm about to say now. And before I say that, let me just draw a picture of this. So typically, the space of Kasner solutions is drawn as a circle, because you can think of it as a sphere intersecting a plane. So here is the circle, where each point on this circle is a Kasner parameter. So this is P1, PD. This is a circle of Kasner exponents. So natural question that can arise is the following. Okay, so we have Kasner solutions. They collapse at time t equals 0. The collapse is very specific, but it is an isolated family. It's a continuous family, but it's an isolated family. So one might wonder what happens if you take the initial data, which still satisfy the condition that trace k initially is positive. So it satisfies the conditions of the Hawking incompleteness theorem. But you can ask, will this solutions which arise from such initial data nearby, so somewhere here, will this initial data lead to solutions that also blow up at some time to the future? And what is that blow up going to look like? So in particular, is it true that you will be attracted, for instance, to another Kasner solution as you go forward, or something else will happen to such initial data? So this is a question of stability of Kasner solutions. Okay. So here, there are important heuristics that were put forward in '85 in a paper by Desmarais and Spindle. Heuristics which tell you the following, that you should expect stability of Kasner solutions. So stability, and I will have to explain what stability in this case means. Stability of Kasner in both models, meaning both in vacuum and in the scalar field model, provided a very simple condition is satisfied. So that condition is the following: that you need to choose 3 arbitrary Kasner exponents. So pi plus pj minus pl, and this expression has to be less than 1 for all choices I, j, and l, which are not equal to each other. This is the condition. So if this condition, if you start with initial data close to a Kasner solution with exponents pi's, where each 3 of such exponents satisfy this condition, then you should expect stability. So let me call this condition star. Now, one important thing to observe immediately is that in vacuum, so when t is equal to 0, in dimension 3, which is the most interesting physical dimension, at least from a classical point of view, this condition is never satisfied. So never satisfied. You can never find such Kasner exponents. Never satisfied. And this is related to the fact that in vacuum, one of the exponents has to be negative. So it's not difficult to convince yourself almost immediately that when d is equal to 3 and one of the exponents is negative, you can never make this combination to be less than 1. This combination will actually turn out to be greater than 1. So when in vacuum, when d is equal to 3, this is never satisfied. And if you're interested in vacuum, it turns out for algebraic reasons, very simple ones, that the lowest dimension in which this condition can be satisfied in vacuum is exactly d equals 10. So that is why d equals 10 appears in this analysis. So in vacuum, in order to satisfy this, in order to have any Kasner solution which satisfies this condition star, you need to be in dimensions 10 and higher. Now, it turns out when you have a scalar field, because of that extra flexibility, so when t is a scalar field, you can find Kasner exponents which satisfy this condition in any dimension bigger than or equal to 3. Okay. So now let me state the theorem. Theorem, and this is joint work with Fournodavlos and Jared Speck. And informally, the theorem says the following: for all perturbations of a Kasner solution satisfying star, the resulting solution well, first of all, it will exist on the interval which starts at initial data -1 and then goes all the way to 0. Then t equals 0 is a singularity. Moreover, you can compute the Krashman scalar. So this is Riemann curvature, 4-dimensional, well, in fact, D+1-dimensional Riemann curvature contracted with itself. That's the Krashman scalar. And it does behave like constant divided by t to the power 4. So that's a strong blow up here. And moreover, you can make statements about how, in what sense, this resulting solution will actually converge back to a generalized Kasner solution. And the statement, so let me make it like this. This is a statement about, on one hand, it's a statement about the renormalized second fundamental form. It turns out that the expression t times kij converges as t goes to 0 to a limiting matrix kij infinity. And the eigenvalues of this matrix, so with eigenvalues, which are pi infinity. Now, here's an interesting twist. This eigenvalues, unlike the Kasner solution, where pi is a constant, this eigenvalues will actually depend on the point x. And this is why I called it a generalized Kasner solution. So there's convergence in that sense. So informally, you can think that near the singularity, our D+1-dimensional metric actually converges to a metric, takes the form, so let me write it like this, minus dt squared plus, and now you see the sum here, t 2 pi I infinity x, well, times some one forms, which depend on x, they don't depend on t. Okay. So asymptotically, as t goes to 0, the solution looks like a Kasner solution, but such that the Kasner exponents may vary from point to point x. It's not difficult to actually show that as t goes to 0, the metric that I wrote here, this metric right here, does satisfy the Einstein equations. Again, as t goes to 0. Okay. So for t close to 0, this is an approximate solution, but as t goes to 0, the x dependence in the exponents pi washes out, and this is a solution. Now, of course, this exponents pi of x, pi infinity of x, they vary with x, but they are still sufficiently close because we considered small perturbations of the initial Kasner solution. They're still sufficiently close to the initial Kasner exponents that we started with. And this is true as long as the only condition that is needed here is that the condition of Desmarais and Noe spindle is satisfied, the stability condition is satisfied. This applies both to the scaly field model in dimensions bigger than or equal to 3 and the vacuum model in dimensions bigger than or equal to 10, where they are allowed. So that's the statement of the theorem. So let me discuss a little bit around this theorem and then give you an idea of how the proof of this theorem goes. Maybe a very, very simple idea. All right, so now it turns out that what with Kasner solutions, and in general what we have been talking about, is part of a more general outlook. So general outlook, which is in fact is older than that paper of Desmarais and Noe and Spindle. And this general outlook goes by the following. So what this theorem describes the monotonic regime of what is known as the BKL picture. So BKL, let me remind you that this stands for Belinsky, Khalatnikov, and Lifshitz. And the BKL picture, the BKL proposal, sometimes people call it BKL conjecture. This goes back to the work that Belinsky, Khalatnikov, and Lifshitz in various combinations did in the 60s and then in the early 70s. It's maybe the defining paper in there is the 3 alpha paper from 1970. Okay, so this is the monotonic regime. Well, it sort of suggests that there is another regime, or at least one more regime. And indeed, we already said that in vacuum, in dimension 3, the stability condition is never satisfied. So what is the fate of those Kasner solutions in dimension 3 in vacuum model? If they don't satisfy the stability condition, they don't fall under the results of the theorem that I stated. So what happens to those solutions? Well, what is expected to happen is that there is an oscillatory regime. Now, not much is known about the oscillatory regime. So what is expected to happen in the oscillatory regime? So let me first of all draw, again, a picture of the Kasner circle. So each point here is a Kasner solution. In the monotonic regime, basically we're expecting the following, that if we take initial data in the neighborhood of a Kasner solution sufficiently close, then as we evolve the solution to the future, then we'll run into singularity, and moreover, we are attracted back to the points on the Kasner circle. Now, these points, they will be spread out. So it's not just one point, because the corresponding Kasner exponents, limiting exponents, they depend on x. So in some sense, you're going to end up somewhere in the neighborhood of the original solution on this Kasner circle. This is the monotonic regime. In the oscillatory regime, the picture is expected to be quite different. You will start, again, you take a Kasner exponent, and you start in the neighborhood of this Kasner exponent. And what this tells you is that the solution is expected to be a chain of heteroclinic orbits connecting different Kasner solutions. And so that chain will look like this. The solution will start near this Kasner exponent. It will travel in this circle to another one. It will get reflected, travel to yet another one, and that will keep traveling like this. So this is a chain of an infinite chain of potentially infinite chain of heteroclinic orbits connecting different Kasner solutions. This is known, so Misner labeled it a mixed master attractor. So the theorem that I stated describes the monotonic regime. The oscillatory regime, very little is known about it. The BKL paper from 1970 drew this picture and postulated that such solutions should exist. And moreover, it made very sweeping pronouncements about what should happen to general solutions that, well, let's say rather generic solutions. Okay, so I'm going to explain this in a second. So let me just give you a little history of this. So heuristics on the oscillatory regime. So this is BKL, a paper from 1970s. The heuristics are based on considering homogeneous solutions of the Einstein equations. So you look at the general homogeneous model, and in that case, in the case of the homogeneous solutions, the Einstein equations reduce to an ordinary differential system of ordinary differential equations, and they made an analysis of this system, some sort of analysis, and they saw exactly this type of picture. So this is a finite dimensional attractor, except that then they made a statement that even though the heuristics are based on homogeneous solutions, in general, you should expect that should happen, the same fate should happen to non-homogeneous solutions as well, where similar to the theorem that I described, this picture will correspond to every point on the circle. So as you evolve, every point on the circle will jump between heteroclinic chains of different orbits connecting different Kasner solutions. There has been a ton of numerical work, so numerics, and there's been a few rigorous works under assumptions of symmetry. So rigorous results. Again, I'm talking about the oscillatory regime, rigorous results. But there are no results without symmetry, so only with symmetry. So with symmetry. There's a lot of work, so I'm not going to be able to mention all the people involved. Let me just mention a few important results in this direction. So there's important work of Eisenberg and Moncrief, early work of Eisenberg and Moncrief. And then there are some definitive results of Ringstrom, which apply to the Bianchi-9 solutions. So these are homogeneous. So this is Bianchi-9, and then also Gaudy, where he did confirm. So in this did confirm the picture that was predicted by BKL. However, like I said, that BKL made this prediction, and based on, so again, this is coming from BKL, they did function counting and concluded on the basis of that, that this is a picture that should be experienced by a generic solution, whatever generic means in this case. But it turns out, so in particular, their statement would imply that generically you should see a space-like singularity, that generically in this type of situation, a collapse is going to result in a space-like singularity. Well, thankfully, that's been falsified, at least for generic solutions. So this is falsified by the work of Theorem and Luck, who showed that there is actually an open set of initial data where the singularity, part of the singularity at least, can be null. So the Fermat law. Very good. So this is the oscillatory regime. And again, let me stress that without symmetry, very little is understood about the oscillatory regime. So far, we understand the monotonic regime, but not the oscillatory one. At least part of the monotonic regime for the models that I described. All right. Now, what about the monotonic regime? What about previous works on monotonic regime? Again, there's been a lot of work, and I'm not going to be able to mention all of them, but so let me get back to the monotonic regime. So I should mention here the following, that probably rephrase this differently. So there's been partial previous results that were proven by Speck and myself, settling different regimes of the result that I described, but not in the generality of the theorem that I gave. So that is to say that the theorem settles the full, what's called the subcritical regime. So for all exponents satisfying stability condition star, we settled some of the regimes previously. This is the most complete result. Now, an important work in this direction was done by Anderson and Randall, where rather than proving stability of solutions corresponding to Kasner solutions, they proved existence of solutions which are sufficiently close to Kasner. So what is the difference between the two results? So in one result, you start, so you take a Kasner solution. So let me again draw a picture like this. So here is you start near a Kasner solution, your initial data, and you evolve the problem forward and see if you're going to end up with a singularity to the future, and what is your solution going to look like at the singularity. Well, there's another way to try to understand the problem by, rather than solving the problem forward in time, you can actually prescribe yourself. In other words, you can postulate that asymptotically as t goes to 0, your metric looks in this form, and then you can try to solve the problem backward in time to obtain a solution. And that's exactly what Anderson and Randall did. So this way, they produced examples of solutions which are different from Kasner, but close to Kasner. So examples of generalized Kasner solutions, but they did not prove their stability. And there are a few other results in the same direction that I'm not going to be able to mention. Very good. So now let me try to give you an idea about the proof of this result. So let me start with heuristics. So remember that the Kasner solution itself, let me just talk for a second, I'm going to talk about vacuum problem. So the Kasner solution has this form. So in particular, the spatial geometry, the geometry of the slices sigma t, it's trivial, it's flat. So spatial slices are flat. So in particular, you don't have to say that they're flat. You can just simply say that if you're going to try to understand stability of the solutions, you can say that it's negligible. So if it's negligible, let's try to look at the evolution equations which describe the evolution of our slices sigma t that I already wrote down before. Let me remind you that the metric of the spatial slices evolves according to this equation. The lapse here is equal to 1, so I can ignore it. So it's if we know the second fundamental form, then we can reconstruct by integrating this equation in time, we can reconstruct the metric Gij. What about the evolution of the second fundamental form? Well, it turns out that we can actually write it in this form. And that is equal to, so again, this is in vacuum for simplicity. So on the right-hand side, you will see a contribution. So my claim is that what you will see on the right-hand side, you will see little o of t to the minus 1, which means that it's actually integral. Where is this coming from? Well, this is coming from the fact that the right-hand side in this equation is represented by the geometry of your three slices. So this is related to the three-dimensional Ricci curvature of slice sigma t. And now for the Kasner solution itself, this is equal to 0. And of course, that is to be expected because for the Kasner solution itself, we know that the second fundamental form Kij is exactly equal to some constant matrix divided by t, which is what this equation will tell you if the right-hand side is equal to 0. Now, suppose that you postulate that the metric G alpha beta is of the form that you think it's going to be. So it's of this form, and then here, so n, this is going to be close to 1. And then the spatial geometry, you simply postulate that it's of the form of generalized Kasner, where let's say it's diagonal, and you have the Kasner exponent, which depend on x. So if you postulate that, and you compute the Ricci curvature of your three-dimensional slices, you will see that in this case, it's going to be proportionate to 1 over t to the power of pi plus pj minus pl, well, for some l. Notice that this is exactly the exponent that appears in the stability condition. And if the stability condition is satisfied, it tells you precisely that this exponent is less than 1, and therefore it obeys what I wrote here on the right-hand side, that it's little o of t to the minus 1, which allows you to integrate the second equation. It allows you then to conclude that the second fundamental, renormalized second fundamental form t times Kij converges to a limit. You can extract the generalized Kasner exponents, limiting generalized Kasner exponents from that, and then you can then claim that you prove stability. Except that this argument is tautological. The spatial geometry is not given to us. We can't think that we can simply compute the Ricci curvature of the three-dimensional slices based on the postulated form of the metric, and then plug it in on the right-hand side of this equation. This is not how one can solve the Einstein equations, but it does give you very good heuristics. It does tell you why this stability condition appears. It's just the condition that the system is what's called velocity dominated. In other words, that the spatial geometries, the contribution of the spatial geometry of sigma t slices is negligible in the limit as t goes to 0. So let me write a simple model, which will a scalar model, which will sort of show to you what this heuristics correspond to. So model. So imagine that we would solve a wave equation. So we have a simple, say, function phi of t and x, and we'll say the following. We expect that phi behaves like log t as t goes to 0. And then we will also assume that the phi satisfies a second order partial differential equation of the following type. So this is a wave equation. So this is a Laplacian x phi is equal to 0. In fact, it's not too difficult to see that what is written here is nothing else but the wave equation for the scalar field on the background given by the metric G, which is nothing else but simply the isotropic and homogeneous metric. Now, let's just look at the different terms in this equation. If we expect that phi behaves like log t, potentially maybe times some constant which depends on x, then every time you differentiate, you take a time derivative. First time you take a time derivative, derivative of phi behaves like 1 over t. So this term, for instance, behaves like 1 over t squared as you go towards t equals 0. And so does this term. It behaves like 1 over t squared. Now, what about this term? Well, again, if you postulate that your solution is of this form, then you see that the Laplacian will only fold on the function a, which is a function of x alone. And so this function simply behaves like log t divided by t to the power 2/3. So what's very tempting to do in this case is to say, well, as t goes to 0, in this equation, the first two terms dominate, and the last term is negligible. And so when solving this equation, we can simply erase it and solve the resulting ODE instead. Again, the problem is the same as I described 2 minutes ago. This is not how you can actually rigorously solve the wave equation. You can prove that phi behaves like log t times a of x by simply getting rid of the last term in this case. Okay, so then how do you turn this heuristics into a proof? All right, so there are a couple of ingredients. The first ingredient is that we need to find a proper formulation of the Einstein equations. And the proper formulation is actually which is tailored for the purposes that we need here, is a little different than I described. First thing that I need to tell you is the gauge condition. This already came up before. So for instance, there is this mysterious lapse that kept coming up in everything that I was doing, and there was never an equation for the lapse. Well, the equation for the lapse appears when you fix what the function what the function t is. And the appropriate gauge, which is traditionally used to study this type of problems, is the CMC gauge, constant mean curvature gauge, so CMC. So we're going to fix the time function to be such that trace of the second fundamental form k is equal to minus 1 over t. It's very convenient. In fact, this is exactly the condition. This is exactly the value of the trace of the second fundamental form that you see for the explicit Kasner solutions. So we can fix this. And that then gives you an additional equation for the lapse, which is an elliptic equation. Now, in the approach in what I described, the basic variables which you evolved were the second fundamental form and the metric Gij, defined relative. I didn't say that, but in reality, you looked at the metric Gij relative to the parallel transported coordinates Ij. Now, in this proof, we use a slightly different set of variables. So variables. It's still the second fundamental form, Kij, but rather than looking at the metric, we're going to look at the structure coefficients. Structure coefficients, which I'm going to call SIJL. And what are those? So they can be computed from Christoffel symbols, gamma IJL plus gamma JLI. All I need to tell you now is Christoffel symbols computed relative to what? What is the coordinate system? It's actually not a coordinate system, but it's a frame. And we are choosing simply a Fermi propagated frame. Gated frame. Orthonormal frame. So let's call it EI. So everything is computed relative to this frame, including the second fundamental form K. Ij refers to the indices computed relative to the this frame AI. And so the same goes for the Christoffel symbols. Of course, the metric, since the frame is orthonormal, the metric is simply the identity matrix. So there is nothing to do there. Instead, we're replacing this by something which lives at the one derivative lower, well, one derivative more than the metric, Christoffel symbols, but in fact, we take in a specific combination of Christoffel symbols, which are the structure coefficients. Very good. So what do the equations look like? Let me just write a caricature. So in this case, it turns out that your system can be written like this. It's an evolution equation for the second fundamental form K. So dtk minus 1 over tk. K is a symmetric two tensor. And then on the right-hand side, you see spatial derivatives of the structure coefficients s plus the nonlinear terms, which are roughly s squared. And then the structure coefficients themselves, they also satisfy an evolution equation. It's dts minus q over t s. And the right-hand side is spatial derivatives of the second fundamental form K plus nonlinear terms, which are roughly of the form K times S. So K is a symmetric two tensor. S, it's a three tensor. And here the coefficient is 1, and I didn't tell you what Q is. And amazingly, so remember that S is actually SIJL, and then this coefficient Q, it's exactly QIJL, which is equal to PI plus PJ minus PL. And that is the stability condition. We know that by stability condition, this is less than 1. So these coefficients, the coefficient here and the coefficient here, tell you how quickly the quantities in question will blow up as you go to t equals 0. This coefficient tells you that you expect K to go like 1 over t. And this coefficient tells you that S is expected to go like 1 over t to the power q, which is less than 1. So that is, if this holds, if you can actually prove that this is what happens, then this would justify the statement that the spatial geometry is negligible compared to the time derivatives. But the problem is that, again, the left-hand side is an ODE. The PDE part comes on the right-hand side. We can't just ignore it. We can't drop it. And so, what is the scheme to control this whole system? And the scheme is a combination of two different types of estimates. So this is high, low Sobolev estimates. So let me start with the high. High estimates. What does it mean? Well, it means is that we're going to do the following. We're going to take the system above, and we're going to differentiate or apply a differential operator to that system. And the differential operator, so let me call this differential operator DAN, and it's of the following type. It's t to the power a times a spatial derivative raised to the power n. And the fact that it's high is simply means that a and n are very large. But very importantly, that n itself is much bigger than a. So we're going to apply DAN to the system to star. We're going to commute this for the equation through our equations and try to control DAN applied to the both K and S and prove Sobolev estimates on these quantities. Now, what is the role of this operator DAN? Well, this part is clear. We're trying to control high spatial derivatives of our solution. What about the role of t to the power a? Well, it serves a double role. On one hand, the fact that a is positive and large tells you that we're actually letting our high derivatives, our high spatial derivatives, to behave worse than as t goes to 0, because we're letting them blow up with a rate 1 over t to the power a, so which seems to be counterintuitive, because of course we want to have very precise control. We want to say that the spatial derivatives are negligible, and so they don't blow up very fast. But the whole point is this condition, that the number of derivatives that we take is much, much bigger than the power of t that we put in here. Now, the second role that this parameter a plays is that when you commute this operator through the equations, it generates a positive good term that will help you get the estimates. Okay. So that's the high part, and the high part will simply tell you, will allow you to conclude in principle that these derivatives, in some sense, in some norm, in some Sobolev norm, will blow up as maybe or a. So this is far from what we want, but it does tell us already that we can control high derivatives of our solution. And so now we need to supplement this with the low Sobolev estimates. And how do we treat the low Sobolev estimates? Well, when we treat the low Sobolev estimates, we go back to the system star, and now we treat the right-hand side as perturbations, meaning that the left-hand side is an ODE, which in principle would give us exactly the estimates that we want, but the right-hand side contained higher derivatives of S and K. Thankfully, because of what we did here, we control higher derivatives of S and K. Now, it is true that they blow up with a very high rate, but the point is that you can add a little interpolation argument to show that the loss that you experience here is still allows you to conclude that these derivatives are negligible. So you need a little interpolation argument. So again, the philosophy is that control high derivatives, allow the high derivatives to blow up fast as t goes to 0. As long as you can limit that blow up to be fixed a, while taking as many derivatives as you can, and then you can show that indeed, for the purpose of estimating low Sobolev norms or the quantities k and s themselves, you can treat the right-hand side as, by the estimates that you proved before, as perturbations, and show that they are indeed negligible. So that's the strategy of the proof. That's the basic argument. And maybe I should stop here.
Okay, great talk. If anybody has any questions, I guess now they can go ahead and ask.
Yeah, hi, Igor. I just have a brief question. So on the slide here, the Pijk, I'm guessing that in this setting, these are the eigenvalues of K?
Which ones?
Pi, Pj, and Pk.
You mean what are this?
What are Pi, Pj, Pk in this setting?
So
or PL?
They're not eigenvalues. So we never work with explicit eigenvalues of the second fundamental form K.
Oh. So how are they defined then?
So you can define the asymptotic values. You can actually show that Kij converges to the renormalized form T times Kij converges to a limiting value, and from there you can extract the corresponding limiting eigenvalues.
Okay. Okay, great. In this argument that you have, does anything survive if that stability estimate is equal to 1 instead of less than 1?
No,
It all
right. So it will not survive. Yeah. So if this combination of exponents is actually identically equal to 1, then you can't handle that.
Yeah. Yeah.
You need this because these terms will become relevant then.
So this serves as the border between the monotonic and the oscillatory regime?
Exactly.
Okay,
Exactly.
great, thank you.
More questions? Okay, if nobody else has any more questions, then let's thank Professor Rodnianski for the great talk. And I guess we should, yeah, we should end here and like see everybody next week seminar. Yeah, let's thank Professor Rodnianski one more time for the great talk. Yes.
Yeah.